and that's it. We begin.
Okay, so it is my pleasure to have the opportunity to introduce my colleague at LUISS, Marco Scarsini, which will present today. So most of you know already him. So Marco Scarsini has a long list of important results from probability in his early career to game theory lately. In addition, he's an important member of Game Theory Society. In particular, time is allocating to young researcher and the numerous co-authors that he has. I know I profited from both of it. So today he will speak about genericity of pure equilibrium and behavior of best response dynamics. So Marco, you have 1 hour. The floor is yours.
Okay, thank you very much. Thank you very much for inviting me to this one-word mathematical theory seminar. I am especially glad to be the first one in 2021 because it can only get better. So this is a joint work with Ben Amiet, Andrea Colavecchio, and Ziwen Zhang. Andrea was a master student of mine many years ago. Ben and Ziwen are his graduate students, so there were 3 generations conflated in this paper with the usual dynamics when there are 3 generations. And okay, so we consider normal form games and some properties of normal form games. We'll see in particular one property. So if you look at these kind of games, some properties hold for all games. So for instance, if you consider finite games and you consider their mixed extension, every finite game admits a Nash equilibrium, all of them. Some other properties do not hold for all games, but they hold generically. For instance, take finite games again. Generically, every finite game has a finite and an odd number of Nash equilibria. What does this mean? It means that, if you take a finite game, either it has a finite and odd number of Nash equilibria, or if not, you perturb it a bit and you get something which has a finite and odd number of Nash equilibria. Some properties are neither generically true nor generically false. For instance, if you consider pure equilibria and you consider the property of admitting a pure equilibrium, some games have it, some games don't have it, but neither one nor the other is generic. I mean, you take a game with a pure equilibrium, take the prisoner's dilemma, you perturb it, still it has a pure equilibrium. Take a game that does not have pure equilibria, take matching pennies, you perturb it, still you get something that does not have a pure equilibrium. So why are we interested in pure equilibria? Well, many reasons. Typically, people consider pure equilibria to be more epistemically founded than mixed equilibria. And in any case, we are interested in pure equilibria from a mathematical viewpoint. So we said before, presence or absence of pure equilibria in game is not a generic property. So how serious is the problem of lacking pure equilibrium? So how frequently, if you want, can I expect a game to have pure equilibrium? So one way to address the problem, to address the issue, is to consider games with random payoffs. Okay? So then you say, okay, I draw a game at random, and I check whether it has or it does not have pure equilibrium. So the issue is, what do I mean by a game at random? So in this paper, we will consider normal form games where the number of players is n, and we'll do asymptotics in n. And every player has only 2 strategies. Why 2 strategies will become clear later on. And we assume that the payoff for each player in every strategy profile is a random variable, and all these random variables are assumed to be IID. So we have a set of independent, identically distributed random variables that correspond to the player or to the payoff of each player in every strategy profile. I will call Cn the game with random payoffs. Now, if the game is random because the payoffs are random, so and the number of players and the number of strategies, 2 for each player, are fixed, but the payoffs are random, so I will have a random set of pure Nash equilibria, which I will denote, which will be denoted by Pne of the game. And we will also consider the random set of strict pure Nash equilibria. Strict pure Nash equilibria are the ones where the inequality holds strongly, the inequality of the payoff that defines the equilibrium. So these two random sets are random. Their cardinality, namely the number of Nash equilibria, of pure equilibria, sorry, and the number of strict pure equilibria are two random variables. We will be interested in the first part of the talk exactly in the behavior of these two random variables. Now, oh, by the way, I forgot to say it. Please interrupt me if you have questions or if something is not clear. Don't wait until the end.
Here's a question, Marco, if I may
Sure.
ask.
Yes.
So why is there, if you have a random game, why shouldn't every pure equilibrium be strict? With high probability, I mean, with almost surely.
Yes, I'll come to that because we do not make the usual assumption that the distribution of the payoffs is continuous.
Ah, okay.
Okay. Thanks for asking, but this is very fundamental question. So, how many pure Nash equilibria do you expect to see in a random game? Well, actually, it's not very difficult to see that the expected number of Nash equilibrium in a random game, in a game with random payoffs, if the distribution of the payoffs has no atoms, so if the distribution of the payoffs is continuous, the expected number of Nash equilibria, or pure equilibria, is equal to the expected number of strict pure equilibria, as Bernard was suggesting right now, and this number is 1. How do you get to that? That's very simple. Assume that you have n players, and even more general than this, assume that each player has k strategies. Okay? So look at a specific strategy profile. What is the probability that that strategy profile is a pure equilibrium? Well, that payoff has to be larger than the payoffs of all the other strategies for every player. So it's 1 over k for each player. There are n players, so it's 1 over k to the n. So the probability that one specific profile is a Nash equilibrium is 1 over k to the n. But how many strategy profiles are there? Well, exactly k to the n. So the expectation is the product of these two is 1. Now, that's the expectation. If you look at the distribution, well, to compute the distribution of the number of pure equilibria in a game with random payoffs is much more complicated. It's more complicated. But there are asymptotic results. So it was already known in the last millennium that as n goes to infinity, as the number of players goes to infinity, the distribution of the number of pure Nash equilibria converges to a Poisson, of course, with parameter 1 because of what we saw before, because we saw that the expected number of Nash equilibria in any game is 1. Now, the question is, how robust is this result? How robust is this Poisson convergence? And the answer is not really, not much. Namely, it relies on all the assumptions of the model. In particular, it relies on independence of all the random payoffs. So more than 20 years ago, Yossi Rinot and myself look at what happens if you weaken a bit the hypothesis. Namely, you keep the hypothesis of IID, of independence and identical distribution, for payoffs corresponding to different strategy profiles, but within the same strategy profile, we allowed for correlation. So we assume exchangeability rather than independence. And we could show that, for instance, if you have a multinormal distribution, when the correlation is negative, the number of pure equilibria goes to 0. If the correlation is, it's not 1, it's 0. It's a mistake. So if the correlation is negative, we have the number of Nash equilibria goes to 0. If the correlation is 0, we get a Poisson approximation as we showed before. And if the correlation is positive, the number of pure equilibria diverges and a central limit theorem holds. Okay?
Marco?
Yes.
Can I have a question here?
Of course, you should.
Some 40 years ago, I recall a lecture by Shapley in Jerusalem on this topic, but I completely don't recall what were his results. Does anybody knows of a result? Did he wrote something on this topic?
Not that I know. I mean, there is a huge literature on that. Several people contributed. I mean, the first papers on existence of pure equilibria go back to the 50s. But
yes.
the name
no, I'm speaking on the case when there is correlation between the random variables.
Not that I know.
This I remember was the main point of his talk. He gave it as the Morgenstern lecture in Jerusalem, but I really don't remember what was the result. And I don't know if he wrote it ever.
Not that I know. I don't know whether Yossi knows it. By the way, I remember that when we started working on this, Yossi told me that Hugh Merrill suggested the problem to him.
Yes, I remember, yes.
Thank you, by the way. Okay, so when you introduce this kind of possible dependence among the payoffs, you see this phase transition behavior. And so
I have another question.
Is not robust. So there were other forms of robustness that have been studied. Daskalakis, Dimakis, and Mosel looked at graphical games with random payoffs, and they looked at the role of the graph in the number of pure equilibria. And here we are looking at robustness in a different direction, which is the one that I was mentioning before to Bernard. Namely, we will look at what happens when the distribution of the payoffs has atoms. So if there is discontinuity in the distribution, and some values can be taken with positive probability.
Can I ask something else?
Sure.
So if a game is symmetric and has 2 actions per player, it's known it has always a pure equilibrium. That's relatively easy to show. Is symmetry something like positive correlation?
In a different way, because there with Yossi we looked at correlation within the payoffs of a specific strategy profile. When you look at symmetry, we are looking at different strategy profiles. But still, yes, it is correlation, and that also alters the robustness of a Poisson.
Okay, thanks.
So why are atoms important? Because when there are atoms in the distribution of the payoffs, with positive probability, two payoffs may coincide. Okay, and that's central to the analysis that we'll perform. So we call alpha this probability of ties. So this is the first talk of the year. For this talk, you have to learn alpha. That's all that I ask you to learn. It's alpha. In the following talks, you learn the rest all the way to omega, but for now, alpha is all you need. Well, it looks I'm lying because there is beta. If you want to learn beta, you can learn beta too, but alpha is what is important because beta, which is the probability that one payoff is larger than the other, is actually a function of alpha. Okay, beta is 1 minus alpha over 2. So alpha is the key here, the probability of ties. Now, it's not difficult to see, applying the same argument that I was applying before for the case with no atoms, that if I look at the spectral number of pure equilibria, this is 2 to the n times 1 minus beta to the n. For the same reason as before, you look at the probability that one specific strategy profile is a Nash equilibrium, is 1 minus beta, is the probability that for that player, that is better than the other payoff. So there are n players, so it's 1 minus beta to the n. I multiply by the number of strategy profiles, which is 2 to the n, you get this. And if you look at strictly pure Nash equilibria, you get 2 to the n times beta to the n for the same reason. Beta to the n is the probability that that specific beta is the probability that that specific payoff is strictly better than the other one. There are n players, so it's beta to the n multiplied by the number of profile, you get this. Now, since 2 times 1 minus beta is larger than 1, you see that as n increase, this value here diverges. And as beta is smaller than 1/2, 2 times beta is smaller than 1. So as n increases, this goes to 0. We'll see something more specific and precise, but you get the picture. Before, as going back to the case we had before, when there are no atoms, beta is 0. Beta is 1/2. 1 minus 1/2 is 1/2. 2 times 1/2 is 1. So this is 1. Okay? And the same here. So in the case of no atoms, the two things coincide and the value is 1. Okay, so this is just the outcome of a simulation for different values of n from 2 to 15. Alpha was 0.5, and you see that the curve 1.5 to the n interpolates very well the values of the simulation. Now, we start looking at strict pure Nash equilibria, and we get the following. When alpha is 0, well, we get the Poisson approximation that we knew about. So the probability of having k strictly pure Nash equilibria e to the minus 1 over k factorial, Poisson. And if alpha is larger than 0, so if there are atoms, with probability 1, the number of strictly pure Nash equilibria goes to 0. Okay. Now, what happens to pure equilibria? Well, we saw before that the expectation diverges, and we have this central limit theorem. So apart from the formula, this says that the number of pure equilibria properly normalized has a distribution that converges to the distribution of a standard normal. But what's interesting is that we can bound this distance, okay? And this distance depends on alpha, you see, depends on n, and on a constant, okay? Okay, if there is time, I can go back at the end about the proof of this. Okay, and this is just a simulation that shows the central limit theorem. Now, a consequence of that central limit theorem is that asymptotically, the number of Nash equilibria, not just the expectation, but the number of Nash equilibria scales with 1 plus alpha to the power n. Okay, so this, what I have done up to now, concerned the number of pure equilibria in this class of games. What we're going to do in the second part of this talk is to look at what happens if I'm trying to get to pure equilibria through some best response dynamics. Okay? To do that, I will use a representation of the game through a graph. And then on this graph, I will do some random orientation, and I will connect that to percolation. So, given a game with n players and 2 strategies for each player, I can associate to this game a graph, okay? A hypergraph, Hn. Vn is the set of vertices, En is a set of edges. So the set of vertices is the set of strategy profiles. And the set of edges is constructed this way. I connect 2 vertices only if and only if I can go from one to the other through a deviation of 1 single player. So 2 vertices are connected if all their entries are the same, except the entry of player I, for some player I. Okay? If this happens, I say that S is connected to T via I. And I say that S is connected to T, is a neighbor of T, if S is the neighbor of T via I for some I. Okay? And I call S T the edge that connects these 2 values, these 2 profiles, S and T. So this corresponds to the, if you want, the 0,1 hypercube of dimension n. Now, given a strategy profile, S, I can look at all the profitable deviations from S. So these are all the neighbors of S, all the neighbors T of S, such that the payoff for T is larger than the payoff for S for the player I when S and T are connected by player I. So this is a set of profitable deviations. Now, we can define on the graph that I told you before a Markov chain that we call BRD. BRD stands for best response dynamics, where you start with some profile S. That's the starting point of this Markov chain. At time 0, we are in S. Then, wherever you are at time k, you pick one of the neighbors that correspond to a profitable deviation. You pick one of them at random, and you move to this one at random. And you call this new profile W. And if there is no profile in the neighbors that guarantees a profitable deviation, then the process stands where it is forever, stays there forever. That means that we have reached a Nash equilibrium. We have reached a point that does not allow for profitable deviations. Okay? we will look at best response dynamics that start at 0. Why 0? Because, you know, in the hypercube, there is symmetry. I just need to start at one specific point. I choose 0 because it's simpler to describe. I could have chosen any other point, but given that I will do asymptotic in n, if I chose any other point, I will have to define an infinite binary sequence and say that I will move in and out that sequence. It's much simpler to say that I start at 0. 0 could be any other point. It's just one fixed point. Now, all that I had up to now refers to any possible game with n players and 2 strategies. Now we go to the case that we were examining before, namely the case where the payoffs are random. Now, remember before, beta was the probability that one payoff of one player was smaller than the alternative payoff for that player if he deviated. So I associate to the random game a partially oriented random graph where the set of vertices is the one that we had before. The set of edges is also the one that we had before, but now we orient some of the edges. How do we do that? If S and T are neighbors, and if the payoff in T for player I are payoff through I, are neighbors through I, and the payoff in T for player I is better than the payoff in H, I draw an arrow from S to T. So I orient the edge from S to T. Now, the payoffs are random, so the orientation that comes from these payoffs is also random. So I have a partially oriented random graph. Why partially oriented? Because some of the payoffs may coincide. So when beta is 1/2, so when there are no atoms, no two payoffs have the same payoff, so no two profiles have the same payoff, so the random orientation is proper. Every edge is oriented one way or the other. But for the case of atoms, two payoffs could be the same, and in that case, there is no orientation on some edge. So some edges are oriented one way, some edges are oriented the other way, some edges are not oriented. Okay, so we will want to use this to look at the probability that the process of the best response dynamic that I defined before reaches a pure Nash equilibrium in a random game. So how do I do this? First, I define accessibility. So I say that E is directly accessible from S if there is an oriented edge that goes from S to T. And I say that T is accessible from S if I can find a finite sequence of profiles, of vertices, such that I can go from one to the other, so that by going, so S is equal to S0, T is equal to Sk, and I can go from S0 to S1, from S1 to S2, all the way to Sk. So in a finite number of steps, I can go from S to T. Now, we partition the set of vertices in this partially oriented graph into two classes, two disjoint classes. This class L is the class of vertices that contain 0, my starting point in the dynamics, and all the vertices that are accessible from 0. And M is the complement of it. So these are the vertices that are not accessible from 0. So I partition the graph the set of vertices in two, the ones that are accessible from 0 and the ones that are not accessible from 0. Let me just give you an example. So this is a, a game with 3 players. Player 1 chooses the row, player 2 chooses the column, player 3 chooses the matrix. And these are random payoffs. They are drawn IID from a uniform distribution between 0 and 1. And these random payoffs produce this graph. So if I start from 0, the green indicate profitable deviations. So there is this profitable deviation that leads me here. And if I take this profitable deviation starting from 0, when I get here, I'm stuck because this point has only inward edges. So this is a Nash equilibrium. Otherwise, I could take the other profitable deviation from 0, 0, 0, I go to 0, 0, 1, 0, sorry. Then I go to 1, 1, 0, then I go to 1, 1, 1. And this, again, is a Nash equilibrium because all the edges are inwards. So this particular game has 2 Nash equilibria, this one, and they are both reachable from this starting point. What we will want to see whether this happens in general. And this is the main theorem of the paper. And as I promised, alpha is the parameter that has the main row. Actually, this is a monologue. It's only one parameter that has a role, and it's alpha. So when alpha is between 0 and 1/2, this happens. When alpha is equal to 1/2, this happens. And when alpha is larger than 1/2, this happens. So there's a clear phase transition in 1/2. Okay? So let me explain what these things are with words rather than with a formula. So when alpha is more than 1/2, if we apply Borel-Cantelli to this formula, we can see that that means that there exists a value n star, random value n star, a random integer n star, such that for all n larger than this n star, so for all games that are large enough, each of the pure Nash equilibria in the game can be reached by the best response dynamics starting at 0. All of them can be reached. When alpha is equal to 1/2, with positive probability, some of the pure equilibria are not reachable. And when alpha is larger than 1/2, the number of pure equilibria that are not reachable via best response dynamics grows to infinity. Okay. So there are plenty of equilibria, but an infinite number of them, a number of them which is larger and larger cannot be reached. Best response dynamics. Yes, madam.
Marco, in C, can you have a better quantification, not just about going to infinity? Can you replace the K with some function of N?
No, all these results are asymptotic, and we don't have. It's a very interesting problem, but no, we don't have it. We just have the asymptotic behavior of that. But yes, it is interesting. Okay, so that was the behavior of the pure Nash equilibria in terms of the best response dynamics. Here we have another slightly different consideration, and that says the following: if alpha satisfies this inequality, which means that if alpha is smaller than this value, about 0.68, then again, by using the first Borel-Cantelli lemma, there exists a random n star such that for all n larger than n star, the process, the best response dynamics, converges to a pure Nash equilibrium. Well, you may think, okay, I mean, this looks trivial because we saw before that, you know, they can be reached at least for alpha smaller than 1/2. But in principle, the thing could get stuck in a trap, okay? And that's the consideration that I'm going to do now. So what do I mean by a trap? So first of all, I call an oriented graph strongly connected if I can go from any vertex to any other vertex. And I call a trap a strongly connected subgraph such that once you're there, you cannot go out. You cannot reach any of the vertices outside this subgraph. So when a process, a best response dynamic process, does not converge to a pure Nash equilibrium, it is because it was absorbed in a trap. Traps are also called sync equilibria. There was a paper by Goemans and others about 15 years ago about sync equilibria. This is, again, a simulation that shows the number of traps for different values of n and for different values of alpha. So when alpha is smaller than the threshold that I indicated before, there are basically no traps. This is for the threshold. And this is when alpha is larger than the threshold. You see there is an exponential growth in the number of traps. Now, what I want to do now for the rest of the talk is to give you an idea of how we proved the main theorem. What are the tools that we used to prove the phase transition in alpha at level 1/2? And the tools come from percolation theory. So let me tell you what, give you just the basic definitions in bond percolation. So we do percolation on the edges. So take this hypercube Hn, and for each edge, you flip a coin that has heads with probability beta. So when you toss a coin, you get heads, you declare the edge to be open. If you get tails, you declare the edge to be closed. And so if you take the random subgraphs that is obtained by considering only the open edges, namely you delete all the edges that are closed, this random subgraph is what is called a percolation. In this case, a percolation on the hypercube. So this subgraph contains all the vertices, but some vertices could be isolated. Or in any case, it contains all the vertices, but this random subgraph could be disconnected, okay? Because some edges have disappeared because they were closed. So we'll use this to give a description, a detailed description of the geometry of pure Nash equilibria. But the trick is that percolation, the way I've defined it here, and the way it's mostly studied, is something that relates to unoriented graphs. So here I'm just looking at the hypercube without any orientation. What we have done before, we have represented the game through a partially oriented subgraph. So we'll have to connect the non-oriented graph that gives me the percolation with the random partially oriented graph that I use to represent the game. And this is exactly what we did. By doing this through some coupling argument, we could prove the following. So take any beta between 0 and 1/2. That's the range of possible values of beta. I can always find a percolation for every fixed n such that the set of components, the set of vertices that are reachable from 0 in the percolation, which I called L beta 0n, coincides with the set of vertices that were reachable from 0 in the partially oriented graph that I used to represent the game. So you already see that there is a strong connection between the percolation on the unoriented graph and the set of vertices reachable from 0 in the partially oriented graph.
Excuse me.
Yes.
I don't understand. Can you go back to
Sure,
the,
yes.
is this a probability statement? What do you mean there exists a percolation? You can say that beta, that you always have heads or always got tails. I don't understand this statement. And is this a probability statement or a construction?
Yeah, it's a probability because beta is the probability that you use to open and close the edges. So basically this says, take a percolation, okay? So that's the random subgraph of the unoriented hypercube.
So it's a random graph.
Yes, it's a random graph. And then take the partially oriented graph that I used to represent the games with random payoffs. Okay. These two things are random. I can couple them in a way that these two subsets, this one and this one, coincide. Does that make sense, Yossi?
It's not easy for me, this statement. I don't know about the others.
No.
Okay, so I have two graphs. The vertices of these two graphs are the same, but the nature of these two graphs is different. One is a graph where the edges are not oriented and can be open or closed. Okay? Delete all the closed. You're left with a subgraph with those vertices and some edges, random. On the other hand, I have a graph with the same set of vertices, with the same set of original edges that I have oriented at random, either one way or the other, or none at all. So this is a random, partially oriented subgraph. Okay. Now, in one graph, I can define this, and in the other, I can define this. So in the unoriented graph, this is the set of vertices that are connected to 0. And in the partially oriented graph, this is the set of vertices that can be reached, that are attainable from 0. Okay? These are two random sets. Okay? They are generated with the same set of vertices, dimension n, the same probability beta, okay, but in different ways. Now I claim.
Marco, when you say there exists a percolation,
Yeah.
so do you mean a realization of this random graph? What do you mean by there exists a percolation?
Exists a percolation, yeah.
I mean that I can put these two things on the same probability space. Okay, if you want this, there exists a coupling such that these two things coincide.
Do you have to say there exists with probability, with positive probability, with probability 1, or that's irrelevant?
Well, if they coincide, they coincide. If you want, they coincide with probability 1. Yeah.
The graphs are random,
So why do you say there exists? Why don't you say the percolation? Why don't you refer to the percolation compared to the there exists? What is confusing here? The two words there exists.
Yeah.
Well, analyze the percolation by itself. Okay.
You have a percolation which is a random graph, right?
Yes.
It's not a realization of this random graph.
No. I have percolation, which is a random graph. Okay.
Okay.
Then on the other side, I have a partially oriented subgraph, the one of the game.
Yeah.
Okay? So another way, okay, maybe let me say.
Well, let me try to pinpoint the question to understand. You say there exists a percolation, so it means that there is a family of percolations. What is the family of percolation by which you say there exists one of them? Because
Well, it's the same
beta is now fixed. So is beta, is B of beta n, is this defined by beta?
Okay.
Is a good question.
Let me say the result in a different way. Maybe this helps. Start with the game, and the game has this. Okay, through the game I can define this. This is the random set of vertices that can be attained from 0. Okay.
Okay.
Then I say, with the same beta and the same n, I can construct a percolation such that these two objects have the same distribution.
Yes.
Okay? Is this more convincing?
Marco,
Yes.
Yes.
I think you want to make clear when you said there exist or things coincide, whether the random variables as functions actually coincide or the distribution coincide, whether the existence is within random variable or distribution or realization.
Marco, I think, do you mean that there exists a probability space?
Yes.
With a mapping, measure preserving mapping to beta of beta n and to L beta 0 n?
Yes, that's exactly what I mean. So
is that the meaning? So there exists means this embedding, yes, from a probability space into this probability space.
Yeah. So the percolation exists by itself. The game exists by itself. Okay. So they could be put. They could live on two different probability spaces. Okay.
Well, maybe in other words, there is a measure preserving mapping from L beta 0 n to L arrow beta 0 n?
No, I'm simply saying. So I have two random objects in general. So let me add something here.
Do you mean they have the same distribution? Something is not clear here by the statement there exists.
Yeah. Okay. So
I think you should forget. I think you should listen to Marco and forget what is written.
Okay. I start with the random object, call it x. For simplicity, assume it's a random variable. Okay. Which lives in some probability space. Okay. And then I have another random variable y, which lives in another probability space. Okay. And if these two random variables have the same distribution, living in two probability spaces, I can find a joint probability space, call it omega double prime, f double prime, and whatever you want, such that on this probability space, there are two copies, such that this is true almost surely. And these are copies. So x has the same distribution as x prime, and y has the same distribution as y prime. So, and that's exactly what I've been doing here. I'll start with the game. I start with the game, okay? The game produces this. Then on a different probability space, I have a percolation. I put this percolation and the game on the same probability space. And on this same probability space, these two sets are equal with probability 1. That's what I'm saying.
Marco, are you saying that in the game graph, each edge, by comparing two things, is either directed or not directed with probabilities beta and alpha, etc., and that's what makes the game graph a percolation?
Not exactly, not exactly, because of the orientation. For the game, I do need the orientation. For the usual percolation, there is no orientation of the graphs. That's the difficulty. So the difficulty in proving this result is exactly what you're saying, Isako. Namely, I need to couple something that comes from an unoriented graph with something that comes from a partially oriented graph. And I cannot just say, you know, if arrows goes this way, if arrows go this way, this is open. If arrow go this way, this is closed, because there is no this way and that way on a hypercube. So this coupling has to be constructed sequentially. So we start at 0, we look at the neighbors, we start with the percolation, we modify the percolation in a random way so that at every step we still have a percolation with that law, but in a finite number of steps, we get to something that allows us to say that these two things are equal. So that's the difficult part, constructing this coupling. But that's all I'm doing here. I'm just coupling things that in principle live in different probability spaces. Okay? So this is the first part, to prove that these two are equal, just equal, with probability 1 if you want. The second part is this. It requires these definitions. So typically, when talking about percolation, people who study these things are interested in the components of this percolation. We said before, you know, when you construct a random graph the way I said before, just by saying the edges can be open or closed with probability beta, you get different components, random components. And in particular, people are interested in the giant component, the largest component of O. So we could call L beta the largest component, namely the vertices of the largest component. And we call the complement M beta. That's called the fragment. You see the difference between what I have here and what I had in the previous slides is that I'm not concerned about what happens starting from 0. I'm just looking at the largest component and its complement, okay? That I call L beta and M beta. So the second result says the following. Again, this is what I get from the graph. These are all the vertices, all the profile, if you want, that can be reached from 0. And this says that with very high probability, this set coincides with the largest component of the percolation. Okay? So before I proved that this coincides with the component of the percolation that contains 0, and now I'm proving that this coincides with very high probability, asymptotically, with the largest component of the percolation. Okay? So when I do this, means that, you know, from 0, I can reach basically almost everything. I can reach most of the other vertices. And to go into the details of the analysis, we used this very recent result by McDermott, Scott, and Withers. This is an unpublished, still unpublished paper of 2020 that basically says that if you look at these components of a percolation, the probability that any of these components be larger than this value is very small, okay? And a particular case of this theorem was actually studied in 1979 by Erdős and Spencer, and they considered the case of beta equal 1/2, namely the case when alpha is 0, so there are no ties. And they proved that if you look at the set of isolated vertices in the percolation, they showed that basically every element in the fragment is isolated. Okay, and we get this Poisson approximation for the number of isolated vertices. Okay, so this is more or less the results and how we got to them. There are several open problems that we think could be interesting to explore. One is, for instance, how long does it take for the best response dynamics to reach a pure Nash equilibrium, even when we know that it does reach a pure Nash equilibrium. Again, these are some simulations. Another problem is what happens when instead of sorry, it's not different number of players, number of strategies. What happens if instead of having 2 strategies for each player, you have more? And this we don't know. I mean, there is a recent paper by Ben Amiet, Andrea Colovecchio, and their colleagues, Kais Hamza, where they deal with 2-person games, and they do asymptotics in the number of strategies and not in the number of players. But even if you want to do asymptotics in the number of players like we do in this paper, where is the difficulty? Well, the difficulty is the following. Assume that instead of having 2 strategies, each player has 3 strategies. Okay? Look at player I, start with the profile, call it A, and so the alternative profiles are B and C. Assume that B is better than A for player I. So there is an arrow that goes from A to B. Assume that B is worse than C. So there's an arrow that goes from A to C. Now, from A to C, there is an edge, but this orientation is not independent on the others. Because if B is better than A and C is better than B, C has to be better than A. So the orientation is given. So we don't know how to deal with percolations when or with random oriented graphs when the orientation is not independent. So, because we don't know which percolation to associate to that. So maybe we need different tools. And also, if we do the things as these colleagues did, and we do asymptotic in a number of strategies, we have a problem. When we're looking at these things with Yossi, one of the nice results of our paper then was that the asymptotic results in the number of strategies or in the number of players was the same. Okay? and we could do it in the same way. Here is totally different. When you do asymptotics in the number of strategies, alpha, namely the probability of ties, is not the parameter, is not the things that count. What counts is the behavior of the distribution of the payoffs close to the supremum of the support. In any case, these are some references. This is our paper, which should appear in Math of War anytime soon. And these are some other references. And thank you very much.
Okay,
Thank you, Marco.
thanks. Are there more questions?
Sylvain, you have a question?
Very stupid question. In percolation, it's the probability at each node are independent.
Yes.
Here it's as
Like
if
each edge. We are doing bond percolation, so it's the probability of each edge.
yes.
Yes.
Here it's as if you were choosing a new game at each node, or what?
In the construction, no, we fix the game, but we alter the percolation. But in the construction, we do exactly what you're saying. To go from one percolation with probability beta to another one that I can couple to get what I want, I do exactly what you say, namely I change things one by one. I start in a node, then I look at its neighbors, the possible deviations, and then I change those, and then I change those, and in a finite number of them, I have changed all of them by keeping the probability distribution of all these the same. So I change the realization, but I keep the probability distribution to be the same, and then I get my coupling. It's tricky.
If there were cycles, this will not work.
There can be cycles, there can be traps, yes.
If you have cycles, you cannot get this independence. I don't see exactly there is some difference for me.
You have this random orientation of the graphs. This random orientation of the graphs could produce a cycle, could produce, for instance, something like that. Take a face of the hypergroup, it could be. And we showed it, there could be traps. Yeah. So when alpha is large, there's plenty of traps. When alpha is small, you're right. We don't expect to see any trap. But when payoffs may coincide,
my point is the following. You choose a game at random, okay? If you move to another node, okay, then you can assume that the payoffs are also random. But if you come back to the initial node, it will not be, it has to be the same payoff that the one you start with. That was my point.
Oh, but each time it's a different player that is changing the payoff.
That's the point. So there is no cycle. If there is a cycle, then you see, you cannot assume that the payoff is now a new.
No, each transition is due to a change of a different player's payoff. So you could have a cycle.
So player one leads me from here to here. Then player two leads me from here to here.
The graph is, if the graph is indexed by the game, that's my point. You choose the game at random and then you have a graph.
Yes.
Okay?
So in principle, I could have had something like that. You know, I start here. Sorry. I go here, then I go here, then I go here, and then I go here. If you change the orientation of this and you make it this way, which could very well happen, with probability 1/2 is one way, with probability 1/2 is the other. If there are no atoms, then you get this cycle. And the orientation of these four edges are independent.
Yeah, but when you are here at these edges, you cannot start again in the other direction. While if it was random, you could. Okay.
No, but wait. I can take with certain probability this deviation or that deviation.
Assume it's, but for a given game, okay, if you choose the game at random, you could say then there are this probability, but for a given game, then this arrow is fixed. I mean, somehow.
Oh yeah, the realization, once you have realized,
Yes,
it's fixed.
yes,
But before you realize it,
I got it. But you cannot have two realizations where one will come back here and change the direction after. It cannot be the case.
In one particular realization, you may have, let's say, two players with payoff, think on the square, 0, 1, at the bottom, 1, 0, to the right of it, 0, 1, to the top, 1, 0, and it's a complete cycle.
so as Emmanuel was saying, so these are the four different strategy profiles. One realization could be this. And this has, no Nash equilibria. And the other realization could be this. And, and this points that way. But, one realization is the realization of the whole orientation of the whole hypercube. I mean, it's not that, when I cycle, then when I get here, I realize this once more independently. If you want, I realize the whole vector of payoffs. This is 1-to-1. Well, not a 1-to-1, but this defines uniquely one orientation for the whole graph. And that's the one I'm using. Within that orientation, then there is an extra degree of randomness, which is the one that allows me in the best response dynamics to use this or that with equal probability. Yes. So for instance, I could stay in a cycle here and then get out of the cycle. But I may, depending on the realization, get stuck in the cycle. Unless we're talking about two different things, Sylvain.
Yeah, maybe it's not the same. Okay, I claim that if you think of a percolation model, okay, and you choose a realization, you may have cycles, and then you start in another direction. This is a possible this is possible in percolation. Okay, if you look at the realization of percolation model, you can have this. Okay, and I claim in your model with the game, underlying payoffs, this cannot be the case. Think of you just take matching pennies, okay? You may have matching pennies in one direction or the other, but it cannot be the case that when you start at the origin, at the initial point, you have the other matching penny game. While in percolation, you have independent at each node. So I don't know. This is something you have to think about.
But also the orientations are independent.
Okay, I have to think.
Marco,
Yes.
can I ask a much more important question?
Please do.
Are there any ski resorts around you?
Everything is closed.
Galit, you
I
can
see the
maybe
snow
cut
in the back.
recording.
Everything is closed.
No termination.